Okay, good morning, everybody. Thank you for coming to my talk. And I want to talk about this theory and applications, current and future. And there's a lot of stuff. I just skip this this slide. This is too many stuff.
Maybe it would be better to have the microphone a
little bit
higher up.
Little bit of
A little bit here.
yes. Nearby.
Closer. Yes.
Okay.
That's maybe.
Or maybe, yeah, hope. Well, we know vortex everywhere. Everywhere. Every day. Everywhere. There's a vortex. Where there's a nature, we cannot avoid it. Yeah. Well, first we need to clear what is the physical meaning of vortex. I think a physical meaning of vortex, I believe less, argument. Less argument. Vortex doesn't mean you have axle. You have axle. Then you have the fluids rotated around this axle. I think this should be very little argument, I think. As I said. Well, the real problem is the vortex direction, the vorticity direction. It's the vortex strength measured by vorticity. This is a classical theory, but it's very questionable by researchers. Very questionable. Well, anybody, if you did some DNS, LES, simulation, turbulent flow, you will find that this is very questionable. Well, we try to give the definition, the mathematical definition. So we need to give some principles. This must be local. When somebody says, we talk hurricane, we talk, tornado, this group, how the vortex become point? Well, for mathematical, we have, suppose, a point, local, a point. So we should be the vector. Vector is the rotational axis. We should have rotation strength. That means how many circles per second. That's what we need. We need is Gaussian invariant and objective. That means the vortex is vortex. That's physics. That's nature. It cannot say in my coordinates it's not a vortex. In the other coordinate it is. No, that should be all the coordinates, independent. That's our, rules or principles. They should be unique. You cannot have 2 or 3 or 4 or 5, definitions, like Q, number 2, number 3, number. Well, you cannot. Only one. Nature is only one. You cannot have many. If we have many, we need a unified. Just like temperature, well, it's not unified, but you have different. Well, then people finally they want to unify. Yeah. So not might be unique. Also, it should be the systematic. That means you have magnitude, you have direction, you have metrics. So the question will happen because according to the textbook or according to the traditional classical theory, the vortex is a vorticity tube. Well, I think this is original from Helmholtz, but when you do the DNS or LES or do the experiment, you will find this very questionable. Is the vortex strength measured by vorticity? Well, that's in the book. That's in the textbook. It is, but it is very questionable. Is the vortex strong when the circulation is large? That's our question. They say, well, this is could be Kelvin theorem is Stokes theorem. That cannot be wrong. So circulation is large, vortex is wrong. Then Helmholtz 3 theories for vortex correct. We talk about a viscous flow, not about the inviscid flow. We talk about viscous flow. Is correct or not correct? That's what we need to discuss about. Well, according to the book, textbook, I just give 2 examples, but they all say, that's the vortex. The vortex, you have surface. The surface line is parallel to the vorticity. All the textbooks say that. Your surface, you have, vorticity, a surface point, you have vorticity. There's a vorticity is parallel to the surface. Well, this is in the book. I don't think the book also, they never tried DNS or LNS. If they tried, they find no. And that's totally no, Yeah. Unfortunately. That's in the book. Well, there's another book. There's a new book. There's not old textbook. They're pretty new. That means even until today or until yesterday, most people still believe the vortex is a vorticity tube, I think. Well, this is Dr. Wu is the author of vortex dynamics, where he said clear, definition 1, a vortex is a vorticity tube surrounded by irrotational fluids. His definition is very clear. He's the author of vortex dynamics. And even encyclopedia, they say vortex is defined by the vorticity in the fluid, which measure the rate. Yeah. It is clear. It is clear most people or classical theory is no question. The vorticity, vortex is measured by vorticity. Vortex direction is vorticity direction. There's no question about, but as I said, we are suspicious if this book right, did any kind of, DNS or experiment work. If they ever did or not did, unfortunately, I don't know. Then we talk, what is the local rotation? We say vortex, we have 2 things, don't forget it. One is axis. What is axis? Second one, what is the rotation angular speed? That's what we need. First, we have this, dv is velocity, we argue the definition 1. A local fluid rotation axis is defined as a vector that can only have stretching along its length. So I give this definition. What means vortex axis? What is that? This axis, only in this point in the axis, the velocity increment is only can be stretching, no rotation, because vortex axis cannot be rotated by themselves. This is important. Some professor suggests it's not a definition, maybe it's axial. Let's just kindly just say it's a definition. Because vortex axis, it cannot rotate it. So you only can stretch it. According to this, we get a dv. dv is the increment of velocity. This is mathematics. This is exact mathematics. If R is eigenvector, where this is 3 by 3 matrix, alpha is a number. That means velocity increment still same direction. That's stretching. The R is eigenvector. Well, this is a mathematical explanation to definition 1. If we accept the definition 1, then we say we find the axle, rotation axis. So what? Eigenvector of velocity gradient. That's fine. This is the what we defined as Liutex. Well, of course, there's a vector, you must have magnitude as well. This is the magnitude formula. And that's the local definition about axis. Well, I just say a little bit, it's not related. Well, some people may question, why you call the Liutex? But the original name is Liutex. First publication in the PUF. But after published couple published couple there is a professor, a Chinese professor, said, the Liutex is given by me, Liutex, because in the meetings, he suggested this different concept. We should give different name. So he suggested we just give the name of Liutex. Well, then we say, sorry, but we just appreciate you give the name, and we published in a couple, 3 papers, we put the appreciation. But we argued about more than half a year. It's not acceptable. So you must publish a paper to apologize. Me, I say, well, I cannot do that. I can. Well, then after the group discussion, says, well, we just change the name, Liutex. It doesn't, it's not your intellectual, right. You didn't give the name Liutex. So then it's quiet. So I explained a little bit why you call it Liutex. Because I give the other name, then people may claim again. Say the name given by me. You are right. Why you call it? Then call it Liutex. Nobody will argue about it. So that's the reason. I need to explain a little bit. Yeah. Well, this is given by, first by Dr. Wang. Well, these are all my students. Sorry, they're given the, explicit, made easier to develop a program. And, well, there's still a question. What is, you talk about a point definition, the mathematical definition. We are interested in the nature, like tornadoes, like hurricanes, something like that. Then we only can discuss about the cause center. Like you have hurricane, you have this cause center. We only can talk about this. So we call it core line. The core line, we have this, I give these rules. So this is the Liutex direction. This is magnitude gradient. If they are parallel, we say this is the core center, water core center. That's global. That's not local. Yeah, that's not local. We give this. Well, this is already we use for the graphics. Then we call the Liutex core line. Well, Liutex core line should be unique. There's a similar mathematical locally maxima. It's also unique. It cannot be said, well, it's not unique, because we use isosurface. Different method, different water structure, different threshold, different. That's not the case. Core line is unique. Well, we say, well, we have 3 generations. First generation is vorticity based. Second generation is eigenvalue based, like most current popular water, like delta, Q, lambda Ci, lambda 2, etc. Well, we talk third generation, it's about, mainly developed by our group. The first generation, we already know that, we already talked about that. This is just vorticity anyway. Very one, very simple, I think, yeah. So, so this is given by Helmholtz 1858. As I said, Helmholtz's paper is written by German. Nobody, we don't know, we understand German. So we only understand the English. So this is a translation of the Helmholtz. We don't know if the Helmholtz is the original idea or not his original. We don't know. We still don't know. So, and apparently, this immediately get the counter examples. You see that? This is laminar channel. Laminar channel, we know the laminar flow, we don't have vortex, laminar channel. But the vorticity could be very large near the wall. So vorticity is large, vortex is zero. How you say is vortex is vorticity? How to say that? One is large, one is zero. How to say that? The boundary layer, same thing, same story. Well, if vortex is measured by the vorticity, so vorticity large, vortex should be strong. Not very large. Zero. Vortex zero. Vorticity is large. That's a contradiction. Immediately contradiction. Well, such too many. Then the other channel. So then other people say, well, the circulation is large. What is wrong? That's correct. Yes, no. You don't believe that? That's the Stuck's theory. Well, Stuck's theory cannot be, wrong or mistake. But you look at this. We just pick a circle. We do the circulation. We calculate the circulation. Well, the circulation could be very large. Circulation could be very large. Laminar flow. Vortex is zero. So circulation, vortex, there's no correlation. No correlation. Yeah. But there's Stuck's cannot be wrong. Well, Stuck's talk is about what? It's about vorticity. Vorticity, is large, not the vortex. Well, that's why I say we can give 1, 2, counterexamples. I said, welcome, give me counterexample. If you give one, it's enough. We don't need two. This is two already. We only need one counterexamples. I should quit, go out of this classroom. I promise. Give me one. But we given this 2018, almost 6 years past. We didn't find any one counterexamples. Nobody give me, at least. Give me one. It's good enough. We don't need to. So, for the classical theory, well, too many does that. Circulation is very large, according to Stuck's theory, but vortex zero. Well, this is also proved by DNS. This is laminar vortex. This is a story. I ask students, because the book says, vortex is what is the concentration? What is the place? What is very large? Well, I just said, can you do that? Measure the vortex. What's the vorticity? Well, he measured, tell me. Totally a different story, just the opposite. In the vortex, the green one is a vortex. The vortex is small. Outside the vortex, vortex is very large. You don't believe it? Please do the DNS. Please do engineering, do the calculation. If I'm wrong. Well, this is just the opposite in the book. The book says vortex is very large. Vortex is what is the concentration? Well, the real engineering, real computation just give totally different story. Just the opposite. Well, this also show that this is the vortex, this is vorticity. Vorticity line is not a parallel, like the book say, parallel to the vortex surface. It's just orthogonal. How orthogonal say vortex is vorticity tube. Where is the vorticity tube? That's the vorticity tube. That's the vortex. They're orthogonal. They're not parallel. Or just the opposite. Oh. Well, we look at that. That's the Liutex. You see, that's the Liutex, the vortex. The vortex surface is parallel. And look at this. That's the vortex. That's the vorticity. That's the vorticity. The line is vorticity. The vorticity is orthogonal to the vortex. How to say the vortex is vorticity? Vortex is vorticity tube. It doesn't make nonsense. Sounds to me. Yes. Oh, 5 minutes. Oh gosh. Oh, you don't follow that one. Sorry about that. I need a quick. And then we talk about a second generation. Second generation where they try to improve that. But the second generation problem is, well, they're all scalar, but the vortex vector. Physical meaning is not clear. What is Q? What is number 2? We don't know. They're contaminated by shear, and they are required threshold. There's threshold. I don't know. For Q, our experience is we can put 0.01. Then we can put 1 billion. So what is the physical meaning of that? We don't know. Yeah, different threshold we will give different. Well, look like this. This we usually use laminar tool. Use the laminar tool. So if threshold is large, negative large, then the vortex breaks down. So our book say turbulence is created by vortex breakdown. But if we change the laminar to become smaller, all the vortex link together. So turbulence is not generated by physics, generated by threshold. It makes sense? It makes sense? The turbulence is generated by threshold. It makes sense? I don't think it doesn't make any sense about that. That's, again, I think, this Liutex give a unique definition. And we look at the contamination. That's the vorticity. If we agree, there's a Liutex is rotation equals C, eta, epsilon as a shear. So vortex actually put the shear together. And I don't have much time. Then delta really is this formula. And the Q have problem. Even Q, it is less than 0, but delta could be larger than 0. So still delta think is vortex, but Q think is no vortex. So the really, Q more problem. The most popular vortex identification method is serious, contaminated by the shear. We have Q, we have number CI is most close to Liutex, but still contaminated by shear. Well, the method I will just quickly, I don't have time. We use the Liutex omega method. This method, good thing, it is, what is the good thing is they're not sensitive. Not sensitive with threshold. You put this omega 0.52 or 0.6, you always get a similar or same figures or vortex structures. You see that? Well, that's clear, very clear. Vortex, structure. Well, then I say maybe more unique is core-line. Core-line method. We need a core. So you see, we do have core. This is all the gradient of the Liutex, and then we do have core. Core is local maximum, and then we get the vortex structure. Well, be careful that it's not threshold, unique structure, unique. That's more important. Yeah, do you see? That's a unique structure to the vortex core line, and I still need to talk a little bit. We talk principal coordinates. So we need rotated this Z to parallel Liutex. We need. That's what we call a principal coordinates. Then we get a principal tensor. This is our principal tensor. In this way, we easily get the decomposition. So this is original gradient. What is the gradient? We can get, we call it the principal form. We get rotation, stretching, and shear. 3. It's different from Helmholtz velocity decomposition and different from Cauchy-Stokes. So they're tradition. They're for the laminar flow, not for turbulence. This is for turbulent flow. And I say, well, this is just a new fluid kinematic. We'll come back to the original XYZ. Well, then this is, I think, is important. So what's the vorticity? Vorticity really have two parts. One part is rotation, or we say rigid rotation. The other part is shear. They're always mixed everywhere. But when we talk about vortex, we need to separate the rotation from shear. There's nothing else. That's a Liutex. So vorticity is a Liutex plus shear. Well, we can look at our results here. You see that? Yeah, this is the vorticity. Then the most part of shear. That's the fluid transition. That's the leg. That's the ring. Leg, of course, almost all the vorticity is shear. Only very little is rotation. We can call the vortex. We can call the shear as a vortex. I don't think we can call it. Yeah. So that's what I say. This is a mathematical formula and correct forever, everywhere, and forever. Vorticity should be decomposed a rotation and long rotated shear forever, everywhere. Well, this is just simplified what's the methods. I think that Liutex is important to turbulent research because we need to we need to quantify, not just quantify. We need to quantify, yeah, and quantify the research. We need to give mathematical definition. But I think since vortex is important, so critical to research or hydrodynamics, aerodynamics, thermodynamics, oceanography, meteorology, civil engineering, space science, so everywhere, astronomy. We must give a good, accurate, definition, unique definition for the vortex. Well, we get comments by several, Costas is here. There's his comments. Yeah, this John, I think, from Cambridge. This Tim from Caltech. Well, they all say as well, Liutex is the only way to define the Liutex. Well, sorry, I have to jump at this. Our collaboration with Tornado people, and then this is the same is here by me. Well, the Liutex just give the exact vortex center. Yeah, that's by their data, their graphics. Yeah, this is it. And then you see that. This is very common in the internet or in the newspaper, but this is by the Liutex. So Liutex is just exactly the vortex center. Yeah. Well, what is it? We don't know. And this is just show the two vortexes come together. Because in the hurricane, there could be 1,000, 10,000 small vortex. Well, current and near future, that's what I say. We might, right now, mostly we do the SGS model, subgrid model. I think Dr. Yu will talk next, after the next talk. That's our kind, and the future plan, something like that. Because of the time limit, I talk a long time, for the students. Well, in this we only half hour, so I cannot talk 2 days. That's what we plan to do. And conclusions, I already talked about. Thank you.